So ACV, autocovariance, AC, autocorrelation. We did the matrix gamma P, and I'll put N there to denote, N by N matrix. I did the simple case where you have a diagonal matrix, that is our standard assumption. But if you want to, generalize this, zero, zero is simply covariance of, A sub t, comma, A sub t, right? Which is covariance. In terms of lowercase gamma, what is the notation for variance? Or covariance. Covariance between xt and xt. I used the gamma notation one time ago. So the notation that we use for autocovariance function is gamma sub h. And if h is 0, I'm referring to variance. So in the general case, the diagonal elements, I can write it as gamma 0, gamma 0, gamma 0, dot, 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 gamma 0. Good. Okay. What about the next element? I'll put gamma here, gamma there, gamma there. All I need to know is to subscript. What should go up here? Covariance is say xt and xt minus 1. A lag of 1. Very good. Lag of 1. 1. Take a guess. The next one. 2. Last one would be n minus. Good. And then you have 1, 0. I'm going to put it as gamma 1 still. And 1, 2. Gamma 1, 1, 3, gamma 2, dot, 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 gamma n minus 2.
So we have that. Why did you?
I think what you're about to ask, you're not saying a pattern.
Yeah.
Right? It is coming. So next one would be gamma 2. That element, gamma 1, over there, to be gamma 1, dot, 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 gamma n minus 3, dot, 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 gamma n minus 1. I'll just put dot, 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 and I don't want to confuse you with the generalized version. So dot, 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 dot. It is unnatural, Joe, because you're not able to see a pattern yet. By looking at this matrix, you will see that the matrix is symmetric. Do we agree? It is a symmetric matrix. And of course, we took linear algebra. If you have to invert a matrix, it doesn't have to be symmetric. but it has to be.
There's
We're going to take linear algebra, right?
somewhere.
It has to be a square matrix. So in this case, we've got symmetric, we've got square, great. Such a cyclic matrix, oh, time t, 0 and 0, lag 0, covariance is simply variance, same time index, variance, same time index, variance, same time index, variance. Good? Okay. What is the lag between that and that? 1. So, 1. Lag between 0 and 2. 2. 2. Lag between 0 and n minus 1. N minus 1. Good? Over here. Lag between 1 and 0. 1. 1, 1. 0. 1, 2. 1. 1, 3. 2. And 1, n minus 1. N minus 2. Good? So, when we have matrices, we generally say I rows, j columns. That is our standard notation. Okay, if I use the row index as I, column index as j, each of those lag values, the numbers that you see, 0, 1, 2, etc., can be represented using I and j. So what is that expression? Omar says absolute value of I minus j. Do we agree? Why absolute value, Omar?
So you don't end up with negatives.
Well, I don't like negativity, but still, mathematically speaking, you can't simply ignore negative numbers, right? The negative part comes from how we subtract. If you simply go with I minus j, here you have 1 minus 0, which is 1. There you would have 0 minus 1, negative 1. But based on the structure, it is symmetric. And not only that, based on our assumption, if I'm at xt, I'm correlating with xt minus 1, whatever correlation that I see there must be the same as xt and 1 step forward. Agreed? They have to be the same. So, hence, absolute value. In other words, if we want to write, you can write it this way. Gamma of h equals gamma of negative h. They are the same. So, long time ago, I sketched the autocorrelation function in R, and we started at 0 and we looked at all positive values of h. I didn't look at the negative side at all. Agreed? There is a negative side. We just don't plot it because it will simply be the same on the other side. Good? So, because of that, we look on the positive side of things. If I have to go from here to that, the autocorrelation matrix, how would this change? So gamma k would be k autocovariance I would like to know what rho k is, which is the k autocorrelation. And autocorrelation is what we want. How do we go from gammas to rhos? Okay, so we know rho k is simply gamma k divided by gamma 0. Yes? So I simply derive this, I'd end up getting 1, 1, 1, dot, 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 1. The rest, rho 1, rho 2, dot, 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 rho n minus 1, rho 1, rho 2, dot, 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 rho n minus 1. And that's it. Of the two, we want to look at the autocorrelation matrix and not autocovariance. I explained this a long time ago, that sure, one can look at autocovariance, but the magnitude of autocovariance does not imply the strength of correlation between two random variables. So just because you have a value of 10,000 doesn't imply that the random variables are strongly correlated. So we want to normalize it, and we normalize, you get autocorrelation, which is better. Good. Okay, do we understand the matrix? We will use this matrix for, lower dimensional cases, maybe AR2, at those, past that, things get complicated. Do we see the connection between this and what we wrote last time? So if there is no correlation at all, then all of those would be 0, and you only have the diagonal elements, which is sigma squared A. So if we have a full matrix, things are heavily correlated, then it's going to take some time. So, good. Okay. I believe I wrote it over here. Last class, that I minus j, j minus I is something that you can't let go, right, in this class. I wrote it here. You can go back and look at that bit. I think so. It was right here somewhere. Because it is the lab, I minus j, j minus I, and everything in time series depends on the lab. Good? Okay. Case n equals 1. What is gamma 1? The dimension of the matrix. 2 by 2. How do you get 2 by 2?
0, 1 by 2.
So you need a 2 by 2 matrix because you're going from 0 all the way up to n minus 1. So 0 would be the first, and n minus 1 will be 0. 0. So error. Still 2 by 2. 1 by. what would that correspond to?
Just simply
It was 0. It will simply be gamma naught. That's it. Right? So this is a case where you have variance and a model where you don't have any correlation. So xt is not related to xt minus 1, or at is not related to at minus 1. Case n equals 2. Now we will have a 2 by 2 matrix. You do have to keep in mind, if you Google this, some might start with 1, some would start with 0. Do pay attention, this is better in my opinion. So 0, 1, 0, 1. You have a lag of 1. Correct. So, what type of model could have an autocovariance matrix of this sort? You go up to a lag of 1. Very good. AR1, is that the only case, Kate? Could it not be NA1? Yes. NA1, another possibility, is the case. Okay. Let's stick with the rows. So now that I know I have gamma 2, uppercase gamma 2, would correspond to that matrix. We are used to that. So let's go ahead and look at these instead. So we'll have 1, row 1, row 1, 1. Okay, positive, semi-definite, all of that. What is the determinant of this?
1 minus p1 squared. 1 minus p1 squared.
P1 row, that's row.
Row.
So these two terms minus those two terms, 1 minus row 1 squared, would simply be the determinant of that matrix. Good. Positive, semi-definite. One condition is that the determinant is greater than or equal to 0. Positive, semi-definite. If I have to say definite, then it has to be strictly greater than 0. Good. Okay, going to rewrite this. 1 greater than or equal to row 1 squared, which would imply row 1 squared is less than or equal to 1. Well, which will give me that condition. -1 less than or equal to row 1 less than or equal to 1. Well, row 1 is autocorrelation between two variables. Going back to linear regression, if you have a random variable y and another x, you are correlating them together, you find the linear correlation coefficient, that has to be between -1 and 1, correct? Same thing. Instead of y and x, you have xt and xt minus 1. So AR1, MA1 will satisfy that condition. A logical extension of that case is this. Case images. The matrix would look like 1, row 1, row 2, row 1, row 2, 1, 1. What goes there? Okay. Using the same logic, what do you think the condition should be? Well, positive semi-definite, this is a condition. So if this happens, we've got stationarity. So there is no way that a series will be stationary if it doesn't satisfy that condition. What about that? If you use the same logic, where would you start? Find the determinant of P3. Okay. How do we find the determinant of P3?
Would be the vector I multiplied by 1 minus rho 1 squared.
Do we know? Oh, I see.
I don't know the shortcut.
1 times determinant of that, so 1 minus rho 1 squared. Minus rho 1 multiplied by rho 1 minus rho 1 rho 2. Last part, determinant of that, rho 1 squared minus rho 2 multiplied by rho 2. This part right here is simply the determinant of that matrix. That part right there is the determinant of rho 1, rho 2, 1. The last part there is the determinant of that matrix. Rho 1, 1, rho 2, rho 1. Well, these matrices happen, they
Here.
so
Here, I don't remember.
you can do the same for the other matrices, but you will end up getting the same answer because it is symmetric. Right. Great. I want this entire determinant to satisfy that condition. Good. Extending the logic. In addition to that, I want this to satisfy that condition I want that to satisfy that condition. I want that to satisfy that condition. Good? So, the entire expression one minus rho one squared distribute minus rho one squared plus rho one squared rho two plus rho one squared rho two minus rho two squared. One minus two rho one squared plus rho one squared times one plus rho two minus rho two squared must be greater than 0. Condition number 1. In other words, determinant of the entire matrix has to be greater than or equal to 0. On top of it, I want the line is that determinant 1 minus rho 1 squared must be greater than or equal to 0. That is coming from make some space. The first expression is the determinant of P through the matrix. Second condition is coming from there. Well, 1 minus rho 1 squared will take me back right here. So equivalent to saying minus 1 less than or equal to rho 1 less than or equal to 1. Good. Moving on to that. Rho 1 minus rho 1 rho 2 has to be greater than or equal to 0.
So why not multiplying in the row 1, that coefficient from?
I'm only looking at the determinant.
Okay.
Right, because that was our initial condition. We started with just the determinant. Another condition, the last bit over here, rho 1 squared minus rho 2 has to be greater than or equal to 0. Good. If all of those conditions are satisfied, then you have state it. Good. Pretty painful. Do you agree? This is just for an AR2 and the A2 case. But what if we have AR5 and A5? Really painful. So, which is why we simply look at constant mean, covariance that is independent of time. Instead of doing all this, one can actually go and look for invertibility. Matrix algebra. Without linear algebra, you can't do statistics, period. I mentioned last time, data is a table. So we need matrices. That will be invertible if that condition is satisfied. Yes? But we have to make an exception. What is that exception? Invertible if that condition is satisfied. We've got to make one exception.
Just guess that the determinant can't equal 0.
The determinant cannot equal 0. I wrote this condition this way because, theoretically speaking, that's what we want. Agreed? However, if the determinant becomes 0, then you can't invert the matrix. That is the mathematical explanation. What is the practical explanation? Well, if row 1 is 0, there is no correlation whatsoever between xd and xd minus 1. What is the point of doing any of this? Right? That becomes trivial. So the exception we make is we take that equal away. Good so far? Yes.
You're solving the derivative, you point out the row 1 squared, and then the second step. In the inside of the parentheses, are you supposed to have 1 plus row 2?
Thank you. 1 minus row 2. Or row 2 minus 1. Good. Yeah, I know. I guess that might take algebra. Good so far? Okay. You might wonder, well, why did we do this? That bit right there is what we're going to use to estimate values of fees, the size, etc. Given a series, one can estimate an AR model using those values. Logically, we have to use the strength of autocorrelation to fit that model. Agree? If you know that xd is related to xd minus 1, autocorrelation has to play a part to tell us how well they are correlated. Correct? So later, when we take a series and try to estimate, you will end up seeing phi1, phi2, phi1, phi2. You will see an expression in terms of fees. Good. Okay, going to do our